Okay everyone, and welcome back. So for this next video we're going to be covering section 4.2, which is the mean value theorem. And just like with the last video, if at any point you want to attempt a problem before I go over it, just pause the video and resume when you are finished. So there are very few theorems that I will ever directly test you on. No, I'm never going to actually ask you to ever recite a theorem, but there are certain theorems that I will directly test you on, and the mean value theorem is one of them. So we'll get to what the mean value theorem is in a little bit, but we do need to first start off with Rolle's theorem, because Rolle's theorem actually does lead into the mean value theorem. So for Rolle's theorem, what that says, it's actually really in specific scenarios. So let's say that you have a continuous function on a closed interval. Where's my pointer? Oh, I gotta actually change the pointer. Hold on. Okay, so for Rolle's theorem, let's say that you have a function that is continuous on a closed interval. And it is also differentiable on all interior points. And the two endpoints have the same y-coordinate. So there's a lot here. It's a continuous and differentiable function on a closed interval, and the two endpoints have the same y-coordinate. If something like that happens, that means there is at least one interior point where the first derivative is equal to 0. Key is at least one. So for example, this first drawing here on the left is an illustration of that. We have a function here that is continuous and differentiable. It is on a closed interval a to b, and the two endpoints a and b have the same y-coordinate. So what that means is that there is at least one interior point between the endpoints where the first derivative is equal to 0. Now this is just one of the instances, it can either go up or come back down, giving us a point where the first derivative equals 0. You can have an instance where the function does go down and then come back up, which also gives you a point where the first derivative is equal to 0. And, if it goes straight across, then you have an infinite number of points where the first derivative is equal to 0. Now it does say at least one point, so this over here is another example where you have a continuous and differentiable function on a closed interval where the endpoints have the same y-coordinate, and there's 2 points where the first derivative equals 0, right there at that local maximum and right there at that local minimum. Now, the key with Rolle's theorem is that the function does need to be continuous and differentiable. As soon as you have a point of discontinuity or a point where the function is not differentiable, Rolle's theorem does not apply. So this is an example where, the interval's closed, but we have a point of discontinuity right here. Because of that point of discontinuity, there is no point, between a and b where the first derivative equals 0. Rolle's theorem did not apply because the function is not continuous for every point on that interval. And then same thing here. Yes, this is a closed interval where a and b have the same y-coordinate, but right there at that sharp point, the function is not differentiable. Because the function is not differentiable for every interior point, there is no point between a and b where the first derivative equals 0. Now, Rolle's theorem is going to lead into what the mean value theorem is. So to kind of give you a sense of what the mean value theorem actually is, we're going to start off with a somewhat realistic scenario, at least a scenario that's in a little more familiar context, so that'll hopefully kind of help you wrap your head around what the mean value theorem actually says and what it means. So let's say that you have a highway, it's a turnpike, and that the entrance and exit have a toll, and the toll records the time that the car passes through. And let's say that the tolls are 40 miles apart. So a driver goes through the entrance toll at 10 a.m. and passes through the exit toll at 10:30 a.m. And let's say that this is a world in which this actually happens. Let's say that a police officer waiting at the exit toll gives the driver a speeding ticket. And what we're going to do is we're going to figure out why. So this obviously has to do with the person's speed, which is related to their velocity. And all we really have is the total distance that was traveled, which was 40 miles, and the total time that was traveled, which was that 30 minutes or 1/2 hour. We do actually have enough information to find what is called the average velocity. And we covered average velocity way back at the very beginning of the course. So let's go through it again. So let's actually find this car's average velocity. They've traveled a total of 40 miles, so that is the difference between their ending distance 40 and their starting distance 0. Divided by the length of time that it took to travel those 40 miles, which was that ending time 1/2 hour, minus the starting time 0 hours. So if you do 40 divided by half, you get 80 miles per hour. So remember, that's his average velocity is 80 miles per hour, which, in most places, this is over the speed limit. So how might that relate to the driver's instantaneous velocity at any given point? So, instantaneous velocity is the velocity at a specific moment in time. It could be higher than the average 80, it could be lower, or might there be at least one point in that half hour where that driver was traveling at exactly 80 miles per hour? Yeah, there was probably at least one instance in that half hour where that driver was going exactly 80. That is the mean value theorem. There is a point where the driver's instantaneous velocity is exactly equal to his average velocity. That's basically the mean value theorem. So here's the technical definition of the mean value theorem. Make sure that you copy this down because you will have to use mean value theorem on the next exam. So let's say that you have a function that is continuous on a closed interval. That's very important, that the function needs to be continuous and the interval needs to be closed. And it's differentiable at every interior point. Mean value theorem actually comes from Rolle's theorem, so the function needs to be continuous, it needs to be differentiable, and the interval needs to be closed. If those three conditions are met, then there is at least one point, again, it comes from Rolle's theorem, so we don't know how many points there are, but there is at least one point, C, on the interior, where the first derivative at C equals the average rate of change between the endpoints, f of b minus f of a over b minus a. So, if you want the plain English version, in other words, if you have a function that is continuous and differentiable on a closed interval, there is at least one point where the first derivative is equal to the average rate of change. There was a point where the instantaneous velocity equaled the average velocity. If you're thinking in terms of graphs, that means that there's at least one point on the interval where the tangent line is parallel to the secant line. So remember, the first derivative deals with the slope of the tangent line, average rate of change deals with the slope of the secant line. There is at least one point where they are parallel. So this is just the mean values theorem stated again, and then here's a picture that goes with it. So here's our closed interval a to b. The average rate of change is the slope of that secant line, and then the slope of the tangent line right here at C. These two are parallel, so that means there is at least one point C where the average rate of change equals the instantaneous rate of change, where the derivative equals the slope of the tangent line. Sorry, the slope of the tangent line, the derivative equals the slope of the secant line. You don't have to necessarily write these down, but the reason why the mean value theorem is so important is because there are a lot of consequences of it. There are a lot of other things that actually come from the mean value theorem. Remember how the derivative of a constant is 0? That's the mean value theorem. The reason? The mean value theorem. So basically means if you have a derivative equals 0, that means it's a constant. This is another one that we're going to use an awful lot when we get to integrals. So if you have two functions that have the same derivative, the only difference between them is a constant. So let's say that we have, f of x equals x squared plus 3, and we have g of x equals x squared minus 5. Well, the derivatives for both f and g are both equal to 2x. So these two functions have the same derivative, and the only difference between them is the constant. We're going to use that a lot when we get to integrals. It's a consequence of the mean value theorem. Also, that intervals of increasing and decreasing, making derivatives positive and negative, that's also the mean value theorem. So if your first derivative is positive, then your function is increasing. If the first derivative is negative, then the function is decreasing. That's a consequence of the mean value theorem. Mean value theorem has a lot of uses, it has a lot of applications, and you will be doing some of them on the next exam. So for this first one, this is a real life application. Let's lapse rate is, we're dealing with, meteorology here. So lapse rate is the rate at which the temperature decreases in the atmosphere with respect to increasing altitude. Because as you get higher in the atmosphere, the temperature is going to decrease. It's recorded in the units degrees Celsius per kilometer, and it is defined as an actual derivative. It's gamma equals negative dt over dz. So negative dt over dz is the lapse rate. It is a rate of change of temperature with respect to altitude. So the independent variable here is altitude z. If the lapse rate rises above 7 degrees Celsius per kilometer in a certain layer of the atmosphere, it indicates favorable conditions for thunderstorms, tornadoes, and other severe weather. We're not actually going to be using this, we're going to be using this 7 a little bit later for comparison's sake, but this is just the cutoff for, okay, if the lapse rate rises above 7, we have potential for thunderstorms and other things. So let's suppose that the temperature is recorded at two different altitudes. Let's say that the temperature recorded at 2.9 kilometers is 7.6 degrees Celsius, and let's say that the temperature recorded at 5.6 kilometers is negative 14.3 degrees Celsius. That's quite a temperature difference. So let's assume that the temperature function is continuous and differentiable at all altitudes of interest. Meaning we can use the mean value theorem for this. If it's continuous and differentiable, and we clearly have a closed interval, 2.9 to 5.6, we can use the mean value theorem. We're going to figure out what a meteorologist can conclude from this data. So obviously the temperature has dropped between these 2 kilometers. Let's see how much it has dropped. So what we're going to do is we're going to first find the average rate of change. We're going to find the average drop in temperature between these 2 altitudes. The average rate of change is simply the change in temperature divided by the change in altitude. So the average rate of change here is going to be the ending temperature, negative 14.3, minus the starting temperature, which was 7.6. And we're going to take that and we're going to divide it by the change of altitude. So the ending altitude, 5.6, minus the starting altitude, 2.9. And we get negative 8.1. So for the lapse rate, the average lapse rate is actually going to be, so gamma equals negative dt over dz. Remember, average rate of change is an approximation of the derivative, so it is going to be negative 8.1, which gives us a lapse rate of 8.1 degrees Celsius per kilometer. Those are the units for lapse rate. Now, last I checked, 8.1 is bigger than 7. So what that means is, remember, this is the average. According to the mean value theorem, because this function is continuous and differentiable, there is at least one altitude between 2.9 kilometers and 5.6 kilometers that has a lapse rate of exactly 8.1. We don't know where in the atmosphere it is. It doesn't really matter. We just know that somewhere between these 2 altitudes, there is at least one layer of the atmosphere that has a lapse rate of exactly 8.1 degrees Celsius per kilometer. That's the mean value theorem. And since that is bigger than 7 degrees Celsius per kilometer, we have the potential for thunderstorms and other severe weather. We don't know where in the atmosphere this is, but we do know that there's at least one altitude up there somewhere that has an instantaneous rate of change of exactly equal to the average rate of change. This next one is a little more abstract, and this is the type of problem that you will have to do, on your exams. This is kind of an important one. So we're going to take the function 2x cubed minus 3x plus 1. We're going to determine whether it satisfies the conditions of the mean value theorem on the closed interval negative 2 to 2. Let's start with that. So remember, in order for the mean value theorem to apply, the function needs to be continuous and it needs to be differentiable. This interval is obviously closed, so we don't have to worry about that. But we need to check, is the function continuous and differentiable, which, yes, it is. It's a polynomial. So since it's a polynomial, it's continuous and differentiable on a closed interval, so yes, the mean value theorem does apply. So since the mean value theorem applies, we're going to find the points where the slope of the secant line is equal to the slope of the tangent line. In other words, we're going to figure out where the derivative is equal to the average rate of change. So we're going to find where the derivative equals the average rate of change. No, I just made it. There we go. All right, so let's start by actually finding the average rate of change. So the average rate of change is going to be the, second y-coordinate, which is f of 2, minus the first y-coordinate, which is f of negative 2, divided by the change in x-coordinates, which is the ending x-coordinate 2, minus the starting x-coordinate negative 2. So if you evaluate the function at 2 and you evaluate the function at negative 2 and you subtract them and then you divide by 4, you get an average rate of change of 5. So 5 here is the slope of the secant line, otherwise known as average rate of change. So then let's actually evaluate the first derivative. So the first derivative is going to be 6x squared minus 3. And what we're going to do is we're going to find where the first derivative, 6x squared minus 3, equals the average rate of change 5, and then we're going to solve for x. So if you, add 3 to both sides, divide both sides by 6, and, please reduce the fraction to make your life easier. And then you take the square root of both sides, you get x equals plus or minus 2 over the square root of 3. So you're just going to take the square root of both sides. And remember, to take the square root of a fraction, you just take the square root of the top, you take the square root of the bottom. So these are the 2 points, positive 2 over root 3 and negative 2 over root 3. These are the points where the derivative equals the average rate of change. In terms of the graph, these are the 2 points where the slope of the tangent line is equal to the slope of the secant line. Remember, mean value theorem does not tell you how many points there are. It just says that there is at least 1 point where the derivative equals the average rate of change, and in this case there happen to be 2 of them. So this last one is another application problem. So this is another, very similar to the, the turnpike scenario that I gave you guys at the beginning. So let's say that you have 2 stationary patrol cars and they are equipped with radar and they are positioned 5 miles apart on a highway. The highway has a speed limit of 55. So, we're going to be comparing this to 55. And let's say that a truck passes through the, passes the first patrol car. Its speed is clocked at 55. Doesn't look like he's speeding. 4 minutes later, the truck passes the second patrol car and his speed is clocked at 50. Now we're not actually going to be clocking, using his speeds that he was recorded, but it doesn't look like he's speeding. He's clocked at 50, then he was clocked at 55. Doesn't look like he's speeding at first glance. So those are his instantaneous rates of change in those particular moments. So at the moment he passes the first patrol car, his instantaneous velocity is 55. At the moment he passes the second patrol car, his instantaneous velocity is 50. Now, I'm telling you right now, the truck was speeding. The truck needed to exceed the speed limit at some point in those 4 minutes. Now, the position of the truck along the highway is a continuous and differentiable function, so we don't have to worry about that. But we're going to prove that he was actually speeding. So this is actually going to be using the mean value theorem. Now, before we use the mean value theorem, most speeds are recorded in miles per hour. The times that we're given here, this 4 minutes, we really need to convert this 4 minutes into hours so that we can actually get we can get an actual average velocity that's in miles per hour, which is a unit that we can actually use. So if you want to convert 4 minutes into hours, you can. You just do a quick little unit conversion. There are 60 minutes in 1 hour. Minutes cancels with minutes, so if you do 4 divided by 6, you could just leave it as 1/15. So let's actually find his average velocity. Remember, these two patrol cars are 5 miles apart, so he traveled 5 miles in 4 minutes. So average velocity is going to be the total distance traveled, which is, that 5 miles, divided by the total time he took to travel, which is that 1/15 hours. And if you actually do this, if you do 5 divided by 1/15, or 5 times 15, you get 75 miles per hour. Remember, that's his average velocity. So even though his 2 instantaneous velocities, that were recorded by the radar didn't look like he was speeding, he was speeding. Because by the mean value theorem, there is at least one point where the truck's instantaneous velocity is exactly equal to 75 miles per hour. We don't know where, but we just know that at some time in those 4 minutes he was traveling exactly 75, which is over the speed limit, so yes, the truck was speeding. So that is the end of section 4.2, the mean value theorem. Thank you all so much for watching, and if you have any questions, please don't hesitate to either email me or send me a message in Canvas. I will also be posting the completed, notated PowerPoints as well, so you have that as a reference. So if you have any questions, please let me know, and I will see you in the next video. Bye-bye.